Hi guys, and welcome to the last lecture for Chapter 15, as well as the last lecture for Module 4. Remember, your test is coming up, so make sure that you have already registered for your exam via Register Blast, if you have not done so already. Now, for the last lecture, we will be talking about one of my favorite sources of energy, just because I think it's so freaking cool, is nuclear energy. We're going to be talking about how nuclear energy works, beginning with the mechanics behind nuclear energy and radioactive decay. Then we are going to be going over harnessing nuclear energy, some of the pros behind nuclear energy, a few of the cons, and whether or not more emphasis should be put on nuclear energy as opposed to fossil fuels. Heads up, in my personal opinion, I definitely think that at least in the short term, as we're trying to bridge the gap between fossil fuels and renewable energy, nuclear energy might definitely be the way to go. But I'll let you decide that. For now, let's dive in. So the mechanics of nuclear energy are a little bit different from traditional chemistry in that instead of looking at interactions between electron bonds, those chemical bonds that we talked about way back in Chapter 2, we are now looking at the chemistry associated with the nucleus of the atom, basically where all of the protons and neutrons reside. That's going to be that little central structure on the conceptual diagram of the atom on the right-hand side of your screen. Nuclear energy is the energy that holds protons and neutrons tightly together inside the nucleus of an atom. Now, we can harness nuclear energy by converting it into thermal energy or heat energy inside a mechanism known as a nuclear reactor. Basically, the electricity obtained from nuclear reactors as a result of burning nuclear energy is known as nuclear power. But let's get into a little bit more of the specifics behind nuclear energy and how it works. Before we can do that, we really need to get into what are radioactive elements and something known as radioactive decay. Basically, what you should know is that the larger an atomic nucleus is, the more unstable it is. This is because it takes more and more energy to hold a nucleus of a very large atom together. Think of it in terms of opposites attract and likes repel. Remember from your introductory physical science classes or intro to physics classes, if you guys have ever taken them, that like charges actually repel each other, so the same charge actually repels one another, and opposite charges attract one another. Now, think of all of those positively charged protons packed tightly together inside the nucleus of an atom. As a result of that need to repel from one another, it takes an enormous amount of energy to hold the nucleus of an atom together. And the more protons and neutrons you stuff into the nucleus of an atom, the more unstable that atom is going to be, because those protons want to blow apart from one another just because of those like charges wanting to repel. So any element with a larger atomic nucleus than lead, so basically any element with an atomic nucleus that has more than 82 protons in it, is what is known as a radioactive element, in that it is actually unstable. These radioactive elements are called that because they actually have protons and neutrons splitting off them occasionally in a process known as radioactive decay. Essentially, what happens here is that there isn't enough energy to really consistently hold that nucleus of that radioactive atom together. So at some point, sooner or later, a little piece of that nucleus, either a proton, neutron, or a proton and a neutron, will fly off. It'll split off from the nucleus of the atom, and in doing so, it will release a particle as well as a tremendous amount of energy. That energy is what we harness when we are talking about nuclear energy and nuclear power. Radioactive elements such as uranium and plutonium serve exclusively as the fuel for nuclear energy. As these atoms split off, they release enormous amounts of energy that we capture in the form of thermal or heat energy, which we then convert to electricity. So we harness the power of radioactive decay in a process that we call nuclear fission. Now, nuclear fission is just the splitting apart of atomic nuclei using some sort of mechanism. And in this case, you can essentially think of nuclear fission as a sped up, automated version of radioactive decay. Under the process of nuclear fission, we bombard radioactive nuclei with neutrons. So essentially, we are bombarding the nuclei of these radioactive uranium and plutonium atoms with neutrons in order to rapidly destabilize them. So in a natural scenario where these atoms would at some point or another eventually break apart and release energy in radioactive decay, we speed up that process by rapidly destabilizing these atoms so they break apart immediately. As they break apart, they release energy in the form of heat energy, and they also release their own neutrons as they break down and split apart. These neutrons are now free to bombard additional radioactive nuclei and continue the process in something known as a nuclear chain reaction. Now, nuclear engineers facilitate this nuclear chain reaction at a very steady and controlled rate, usually with the input of water or graphite as a way to moderate the neutrons and keep things from getting too out of control. So they moderate a nuclear chain reaction and allow it to constantly release a steady amount of thermal energy, which they can then convert into electricity, which powers our homes. This is essentially how nuclear energy works. Now, remember how we talked about the only fuel that can be used in a nuclear reactor for the generation of nuclear power is going to have to be a radioactive element. Most radioactive material used for nuclear power generation is going to come from something called enriched uranium. Now, raw uranium, already a radioactive element, is mined deep underground. However, almost all uranium, about 99%, is going to be a substance known as uranium-238, meaning that this uranium has a total of 238 protons and neutrons combined. Now, if you remember from your basic chemistry, all elements basically have to have the same number of protons. And an isotope, if we remember way back in chapter 2, is going to be two different atoms from the same element that have differing numbers of protons. So what we have to do is convert uranium-238 to a substance known as uranium-235. Basically, we have to strip 3 neutrons from this raw uranium that we pull from the ground. The uranium-235 is needed to maintain the nuclear chain reaction because when we burn uranium-235, it emits enough neutrons to facilitate that nuclear chain reaction. So basically, when we take uranium from the ground, we enrich the uranium by increasing the concentration of uranium-235, basically by stripping neutrons from a small amount of the raw uranium, the uranium-238 that we mine from the ground, in order to convert it into usable nuclear fuel and usable nuclear energy, so that we can actually facilitate a nuclear chain reaction. Now, there are some pros and there are some cons to using nuclear energy. On the pro side, some of the serious advantages of nuclear energy include that it is much, much cleaner than fossil fuels. Once we have actually built the facility for housing the nuclear reactors and actually built the nuclear power plant, nuclear energy does not emit any CO2 or any air pollution whatsoever. Scientists estimate that if nuclear energy replaced all fossil fuels for electricity generation, it would reduce emissions by 2.5 billion tons of carbon dioxide emitted per year. That is a staggering amount. And in addition, nuclear energy is far more energy efficient from a volume standpoint as opposed to fossil fuels. Basically, 1 gram of uranium generates approximately 8,000 times as much energy as coal or oil. That is an insane amount of energy compared to coal or oil. So nuclear energy is far more energetically dense because it is a fundamentally richer energy source. Now, there are some drawbacks associated with nuclear energy. One is nuclear waste buildup. As we break down this nuclear fuel into other radioactive elements and radioactive waste, we don't really yet have a great way to store it. Now, this is sort of being mitigated as we speak in that we are slowly building a very long-term nuclear waste housing facility in an inert desert where even if the radiation leaks out, it can't really damage anything. However, until those nuclear waste storage facilities are actually built and generated, most of this nuclear waste is stored in intermediate facilities which aren't necessarily as safe as we would like them to be. So until we get a permanent housing scenario, nuclear waste buildup is actually a problem that we need to learn how to fix. However, nuclear waste buildup isn't as severe as a lot of people like to make it out to be. Nuclear energy doesn't generate nearly as much waste as we think it does. In fact, the amount of nuclear waste generated from one person's electrical use over their entire lifetime could fit in about a cup. So again, this stuff is incredibly energetically dense. In addition, the more severe drawback associated with nuclear energy are the fear of catastrophic meltdowns. This has already happened in the past, and it has happened in the recent past, as recently as 2010 with the Fukushima reactor in Japan. We're going to go over the 3 biggest nuclear meltdowns in history, and we're going to discuss what happened and what went wrong in each one of these scenarios. Before we can really talk about the catastrophic nuclear accidents that have happened in the past, we need to go over exactly what happens when a nuclear reactor gets out of control. Remember how we talked about that nuclear chain reaction. Basically, as the nucleus of one radioactive element decays, it splits off energy as well as byproducts such as neutrons, which then bombard other radioactive nuclei and facilitate the nuclear chain reaction. So it keeps going and going and going. Now, nuclear reactors control this nuclear fission at a stable rate so that nothing gets out of control. It's not an exponential increase of how many atoms are radioactively decaying at any one time. It happens at a slow, constant, controlled rate that we can control and get a steady output of energy. Normally, we do this by inserting something called a moderator. A moderator is a substance such as water or graphite, which is used to slow the nuclear reaction. Basically, by having these substances inside with the radioactive rods, they soak up and absorb the neutrons, so the neutrons don't stimulate and destabilize too many radioactive nuclei at any one moment. Problems arise when nuclear fission becomes out of control and that nuclear chain reaction can actually break away and become incredibly unstable. Basically, too much nuclear fission results in massive amounts of heat energy released, which can trigger something called a meltdown. A nuclear meltdown is a process where a runaway nuclear chain reaction, that is, a nuclear chain reaction that has gone out of control, actually reacts and begins to melt the nuclear fuel rods which are generating the nuclear chain reaction. Once this nuclear fuel is melted, so it's no longer in a solid state, it is now in a liquid state, it can actually become so hot that it actually escapes the nuclear containment casing and then gets exposed into the larger environment. This is a serious problem because once the nuclear material is actually released into the environment, it can interact with different ecosystems around us as well as human health. Now, we have had 3 major nuclear accidents since we began using nuclear power plants, and we're going to go over the specifics behind each one and why different combinations of mechanical error as well as human error led to these nuclear power plant meltdowns and these nuclear power plant problems. The first major nuclear incident happened in 3 Mile Island in 1979. Basically, a combination of human error as well as mechanical error led to something called a cooling failure. Basically, there wasn't enough water circulating to keep the nuclear energy or the nuclear fuel rods cool so they could stay in a solid state. A running theme behind nuclear catastrophes is that the nuclear fuel rods have some sort of cooling failure associated with them, and as a result, the nuclear fuel begins to melt, and that melted fuel rod somehow escapes its casing and ends up into the outdoor environment where it can impact ecosystems as well as human health. Basically, in this case, the radioactive material predictably heated up and triggered a meltdown where it was, in this case, controlled, and minimal amounts of nuclear material actually escaped into the open environment. So the 3 Mile Island incident in 1979 is mostly regarded as a near-miss scenario as far as nuclear catastrophes go. While there was an extremely expensive nuclear cleanup that took decades to take place, there wasn't any serious environmental catastrophes that took place, and there wasn't any human health catastrophes that took place as a result of this nuclear reacting failure. The next nuclear incident that occurred happened in 1986, and this was the Chernobyl nuclear reactor accident. This is regarded as the worst nuclear catastrophe of all time. It is the most extreme nuclear disaster that has ever been recorded in a number of different ways. Basically, what happened here was that engineers actually turned off all of the cooling mechanisms as part of a safety test procedure in order to test new safety mechanisms and backup cooling generation. But something went wrong with the mechanical backup system, and as a result, a massive nuclear meltdown was triggered when not only did the nuclear fuel rods explode, but they also heated up the steam coolant to where the entire ceiling and roof got blown off the nuclear facility, and enormous amounts of radioactive material and radioactive waste were blown up into the air where they could hit the atmosphere and travel for hundreds and hundreds of miles. That nuclear material immediately killed about 31 people within the next 3 months from immediate exposure to radioactive material, and killed as many as 6,000 people from indirect thyroid cancer as a result of the Chernobyl nuclear accident. Again, this is regarded as the most extreme nuclear disaster ever, and this was one of the reasons that nuclear energy has sort of been discouraged over the last few decades, simply because we don't want a recurrence of something like this happening again. Most recently, the nuclear facility that most recently underwent a nuclear catastrophe was the Fukushima Daiichi nuclear facility in Japan in 2011. What happened here was a 9.0 magnitude earthquake, so a massive earthquake, struck the eastern coast of Japan. The earthquake managed to shut down all of the power to the nuclear reactor, so all of the nuclear coolant, the water that was supposed to cool the nuclear fuel rods, immediately began to fail. However, the tsunami resulting immediately after the earthquake dealt a double whammy in that it also shut off the nuclear power plant's backup reactors. Without power, the unattended radioactive core immediately began to heat up and melt down. It triggered meltdowns in not one or two, but 3 nuclear reacting facilities. Now, most of the radioactive material actually went into the ocean, so there wasn't an immediate impact to human health, but it did untold damage to ocean ecosystems, both in the immediate coastal realm as well as in the deep ocean. We don't really know some of the long-term extent of what this nuclear material is doing to the benthic ecosystems in the deep ocean. So as a result of these aforementioned nuclear catastrophes, as well as concerns over waste disposal, growth in nuclear energy has really slowed in the last few years. Basically, all of these nuclear accidents have really contributed to public anxiety about nuclear meltdowns, and fear of nuclear meltdowns has really stalled the additional construction of nuclear power plants. In addition to all of this, the nuclear power plants can be very expensive to maintain. There are a lot of different safety measures that have to be in place, and they're usually very, very expensive to continue to upkeep and implement. As a result of these factors, nuclear energy, or the construction of nuclear power plants, has plummeted in recent years. The question is, should we be looking to nuclear energy instead of away from it? There are still enormous pros in terms of utilizing nuclear energy as opposed to using fossil fuels. Nuclear energy still remains one of the few viable alternatives for electricity generation. For example, one of the big issues associated with renewable energy is that there's no real way to store them. After the sun stops shining and after the wind stops blowing, we no longer have consistent access to energy. Coal is really reliable in that it provides what's called a baseload energy for electricity generation. Nuclear is one of the few alternatives that can actually step in and provide that baseload energy. In addition, nuclear is often less extensive in terms of the damage to surrounding ecosystems. There are no CO2 emissions whatsoever after the nuclear power plants have actually been built, and there are no long-term health impacts associated with a nuclear power plant under its normal generation. Contrast that to any coal-burning power plant, which produces enormous amounts of air pollution as well as CO2 emissions. So again, there are some serious pros to nuclear energy as a viable alternative to fossil fuels. However, caution for nuclear energy is well warranted. While we have come a long way technologically from the 1960s and 1970s, Fukushima Daiichi from 2010 and 2011 kind of shows that we are still vulnerable to some nuclear catastrophes. So that risk is something that we're going to have to consider if we're going to implement or if we're going to increase implementation of nuclear power plants. However, as a result of nuclear energy being one of the few viable alternatives to coal power plants, many environmental advocates strongly recommend building more nuclear energy power plants with increased safety regulations until we can really find a good storage mechanism for renewable energy. So, nuclear energy still has a lot of potential as a sort of stopgap or bridge mechanism until we shift completely from fossil fuels all the way to renewable energy. Now, that is everything we have for the nuclear energy and nuclear power plant lecture. And this is also the final lecture for Chapter 15 as well as Module 4. Good luck on your exams next week, and as always, let me know if you have any questions about any of the content or material. See you next time.